Alrighty, in this video we are going to be talking about Maclaurin and Taylor polynomials. And essentially, as we begin Unit 3, our main goal is to approximate the behavior of ugly functions. So sine of x, cosine of x, e to the x, and ln of x, and make them prettier by making them as a polynomial. So a Taylor polynomial is generated by f at x is equal to a, which is going to give you this lovely polynomial right here. I know it kind of looks messy and scary, but it's not that scary, I promise. So essentially, you're going to have the first term at a. Then you're going to have the derivative at a, and then you're going to have x minus a. So this is the first exponent. I might have 1 factorial right here just so that you can see it. Then you're going to have the second derivative, and then you're going to have over 2 factorial of x minus a to the second power. The third derivative over 3 factorial of x minus a to the third power, and so forth, so that you have the nth derivative over n factorial of x minus a to the n power. Now, this might be a good idea to memorize the first couple of factorials. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and 5 factorial is 120. Will you need 5 factorial? Probably not. Maybe we'll stick with the first 4 in terms of memorizing them. So 1, 2, 6, and 24. Now, a Maclaurin polynomial is a special case where the center is 0. So instead of x minus a, I just have x minus 0, or in this case, x. So you have your first term at 0, your derivative at 0, and then you have your x. Your second derivative at 0 over 2 factorial of x squared. Your third derivative at 0 over 3 factorial of x to the third power, and so forth. All right. You'll notice that these right here are going to be your coefficients, which is going to be very important whenever we work on, let's say, problems 4 and 5, whenever we want to find the value of something. But we'll talk about that whenever we get to 4 and 5. All right, so here's what we're going to do. We are going to find a 4th degree polynomial that approximates the behavior of ln of x plus 1 at x is equal to 0. Here is ln of x plus 1 in black, okay? And we are trying to approximate the behavior at 0. So notice how here, this polynomial in red, or in this case blue now, is my 4th degree polynomial. And notice how if I were to zoom in, it's kind of straight dab in the center of this graph. So it's kind of close to the behavior of ln of x plus 1. We're going to ignore this part because this isn't really at 0 here, so I really don't care about that. But I care about how close this is at 0 with ln of x plus 1. So to do that, I need a couple of things. I need my term 0, or not my term 0, my first term at 0. So I have f of 0, which is ln of 1, which is just 0. Now, since I want a 4th degree polynomial, this means that I'm going to take my derivative until I hit the 4th derivative. Okay, so I'm going to take the first derivative, and that's going to be 1 over x plus 1, which can also be rewritten as x plus 1 to the negative 1. I'm going to take my second derivative, and I'm going to use power, so negative 1, x plus 1 to the negative 2. I'm going to take my third derivative, and that's going to be 2, x plus 1 to the negative 3. And then if I take the 4th derivative here, I'm going to get negative 6, x plus 1 to the negative 4. Now, it's going to be me plugging in x is equal to 0 now for my first derivative, my second derivative, my third derivative, and my 4th derivative. You'll see that this was 0. This right here, if I were to plug in 0, that's going to be 1 to the negative 1, which is just honestly 1. Same thing with this one right here. 0 plus 1 is 1. 1 to the negative 2 is just 1 times negative 1. Same thing here, that's going to be 2. Same thing here, that's going to be negative 6. All right, so to write my Maclaurin polynomial, since my center is at x is equal to 0, I'm going to have my function at 0, which is 0. Then I'm going to have my next term, and that's going to be my first derivative. In this case, it's 1. And then I have x. My next term is going to be my second derivative. That's going to be minus 1 x, the x squared, over 2 factorial. I have my third derivative, which is at 2. So plus 2x to the third over 3 factorial. And then I have my fourth derivative, which is negative 6. So negative 6x to the fourth, 4 factorial. And this right here is going to be my polynomial p of x. In this case, if I want to be very specific, I could say p subscript 4 of x to denote that this is my 4th degree polynomial. So this right here essentially represents this red graph you see on the right. Now, can you keep it like this? Yeah, but for practice, let's say that this is on the MCQ and you probably might need to simplify this. Remember, as our little trick right here, 2 factorial is 2, 3 factorial is 6, and 4 factorial is 24. So this right here is going to be x minus 1 over 2 x squared. 3 factorial 6, so 2 divided by 6 is 3, so I have 1/3. And then I have 4 factorial, which is 24, 6 over 24, which is 1/4. So this right here represents my 4th degree Maclaurin polynomial. That's going to approximate the behavior of ln of x plus 1 at x is equal to 0. All right, I'm going to do number 3 now because number 3 is going to be a Taylor polynomial that is centered at x is equal to 2. So notice how here, this is x is equal to 2, and we are going to approximate a 3rd degree Taylor polynomial. This red graph right here represents a 3rd degree polynomial. It doesn't really look like it, but I promise you it's a 3rd degree. Yeah, like that. It's a 3rd degree at 2. So notice how at 2, my red graph, aka my graph that I'm trying to approximate, is going to be almost the same as my original function of 2x to the negative 2. Since I have a 3rd degree Taylor polynomial that I want to find, this means I'm going to stop at my 3rd derivative. But first, I need to find the function at 2. So I want to find out what f of 2 is. That's going to be 2 to the negative 2, which is going to be the same thing as 2 over 4, which is 1/2. So I'm going to need that. Next thing that I need is going to be my first derivative. That's going to be negative 4x to the negative 3. My second derivative is going to be 12x to the negative 4. And then my third derivative is going to be negative 48x to the negative 5. All right, so if I am plugging in 2, this is going to give me negative 4. 2 to the third is 8, so this is going to give me negative 1/2. This right here is going to be 12. 2 to the fourth is 16. So 12 over 16, 4 over 4 is 3/4. Then I have negative 48 over 32. Let's try 8. Okay, not 8. Let's try 16. So this would be negative 3/2. All right, so we have all the information we need to make my third degree Taylor polynomial. In this case, I'm going to start at my first term, which is going to be 1/2. My next term is going to be my first derivative, so that's going to be negative 1/2 x. My next term is going to be 3/4 plus 3/4. Oops. Now, totally messed that up already. Since we have a Taylor polynomial centered at x is equal to 2, I should have x minus 2 right here. Then I'm going to have 3/4 x minus 2 to the second power because this is my second derivative. And don't forget about my 2 factorial right here. 2 factorial, remember, is the same thing as 2. So 4 times 2 is going to be 8. That's going to give me 3/8. And then I have my third degree, or my third derivative, which is negative 3 over 2 x minus 2 to the third power. And we know that 3 factorial is 6. So 2 times 6 is going to be 12. But then if I simplify that even more, that's going to be negative 1/4. So this right here is going to be my Taylor polynomial approximation for 2x to the negative 2 at x is equal to 2. And of course, on the FRQ, you didn't need to simplify, so you could have left it as the nasty part of this, which is, let's see, 3 over 4 plus 2 squared, 2 factorial, minus 1, 4 times 3 factorial, that. This looks prettier, so I'm just going to keep it as this, as it might show up on the MCQ or something. Okay. For number 4 and number 5, we want to find the value of a derivative. In this case, for number 4, we want to find the fourth derivative at 0. And then for number 5, we're going to find the second derivative at negative 2. All right. So for number 4, we have p of x is a fifth degree Taylor polynomial for the function about x is equal to 0. And we want to find the value of the fourth derivative at 0. I'm going to show you the long way, aka the old-fashioned way, aka me just straight up taking the derivative 4 times. So my first derivative is that lovely thing right there. My second derivative, okay, 32 times 3. I did not do this. That's 96. My third derivative, okay, 96 times 2. And then my fourth derivative, right here. Now we want to find the fourth derivative at 0. So if I'm going to substitute in 0 right here, this lovely 240x is going to become 0. So this means that my fourth derivative at 0 is going to be negative 192. And that was me using the old-fashioned way. Now, there is a much quicker and efficient way, and that's going to be looking at our coefficients. This is asking me the fourth derivative at 0, and if I were to go back to my lovely generic function, this is my generic function right here, and this is my coefficient. So this right here tells me that I'm going to have the fourth derivative of, what was it? 0. So I'm going to have the fourth derivative of 0 over 4 factorial, and this is going to be my coefficient. Now, this right here is going to be my fourth degree exponent. So I'm going to find my fourth degree exponent. In this case, my coefficient of my fourth degree exponent has a -8. So this means that I have a coefficient of -8. And this -8 has to be equal to the fourth derivative of 0 over 4 factorial. Well, that's just going to be me multiplying 8 and 4 factorial together. And we know that 4 factorial is going to be, if I remember, that's going to be 24. So now I have the fourth derivative at 0 being -8 times 24. And if I were to calculate that, we're going to get -192. So using the old-fashioned way works, but obviously there might be some algebra errors if you do it this way, because it's a lot of using power rule whenever we can look at the coefficient and match it up with the rule that we have here. Likewise, same thing with number 5. I want to find the second derivative at -2. And this tells me that I want to look at my exponent of 2 and see what my coefficient is. So in this case, if I have an exponent of 2, my coefficient is going to be -3 over 25. That's going to be equal to my second derivative over 2 factorial. If I solve that, I'm just going to get -6 over 25. So that's going to be my answer there. Now, can you do power rule with this? Sure, if you want to. But obviously the safer way is going to look at my Taylor polynomial and call it a day. All right. Same thing with number 6. I'm going to show you the old-fashioned way, and then I'm going to tell you the little trick on number 6. We have a function f approximated at x is equal to 1 by a third-degree Taylor polynomial, and that gives us this lovely thing right here. And we want to determine whether the function f of x has a local max, min, or neither. That should say min, not minimal. Or neither at x is equal to 1, and we want to justify our answer. All right, so what I'm going to do is go ahead and take my first derivative of this. And I'm going to set this equal to 0. It's going to be very important for you guys to learn your algebra skills and factoring out stuff, aka don't expand this out right here whenever we could just factor out an x minus 1. Okay, now simplify whatever's in the bracket. That's 19. So I have 19 minus 15x, which means that I have a critical point at 1 and a critical point at 19 over 15, which is kind of a little bit greater than 1. Now, here's your next trick. I'm not going to plug in 0, and I'm not going to plug in some number that's between 1 and 19 over 15 because I don't know what 19 over 15 is. But what I do know is the end behavior of this lovely quadratic function right here. This quadratic function has a negative leading coefficient, which means my parabola is going to open down. So it's going to look like this, which means that I have negative and positive, which means that at x is equal to 1, I'm going to have a local minimum. To justify your answer, you're going to say f of x has a local minimum at x is equal to 1 because f prime of x changes signs from negative to positive at x is equal to 1. Once again, this is your old-fashioned way in terms of doing this problem right here. Now, because this says it's a Taylor polynomial, what I'm going to do is think about what my derivative is in terms of my coefficient. Because remember, here, I could find the derivative based off of my coefficients at, in this case, 1. My problem here for number 6 is that I don't have a degree of 1. Because I don't have a degree of 1 term, this basically tells me that my derivative, aka f prime of 1, is equal to 0. Which makes sense because we kind of saw that right here whenever we were doing our critical points. So, based off of that information and nothing else, I'm going to use a second derivative test to figure out if I have my function being concave up or concave down. Well, my second derivative test requires a second derivative. Guess what? I have a degree of 2, which means that I could find my second derivative using my rule that we did for number 4 and number 5. So now I'm going to have, let's see, my second derivative over 2 factorial, and my coefficient is 2. To find my second derivative, I'm going to multiply by 2 factorial, aka 2. That's going to give me 4. All right, 4 is greater than 0. So this means that our function is going to concave up at x is equal to 1, which means I have a relative minimum. So to do your justification, you're going to say that f prime of 1 is equal to 0. So by the second derivative test, f double prime of 1 is greater than 0. So f of x concaves up at x is equal to 1. So f of x has a relative minimum at x is equal to 1. And call it a day. So the one right here is going to be your old-fashioned way back in Unit 3 in AB, where we found the critical points, made a sign chart, used our lovely justification using the first derivative test. The pink one right here uses the second derivative test because we know that the derivative at 1 was 0. Great. So we could use the second derivative test there. All right. In the next video, we are going to talk about 1 over 1 minus x. We're going to talk about e to the x. We're going to talk about sine of x. And we're going to talk about cosine of x and why they are so special. These 4 functions right here, we are going to derive the Maclaurin polynomial, and then we'll use them for the rest of the unit. And then maybe I'll make a third video on the FRQ. We'll see about that.